Right, hello everyone, it's Mr. Tickner here, back in the wonderful world of YouTube videos. To start with, we're going to talk a little bit about forces and the common forces that we identify before focusing in on one of them in particular. So let's imagine that we have a slope and we've got a box on this slope, and because of this I'm going to draw my box in red. Fantastic, I've got a box. And what I've got is I've got a sort of a rope that's connected to this box, and this box is basically being pulled up by this rope. And what we can think about in many respects is what forces can we identify that are just acting on this object. So what forces are on this, and what forces do we currently sometimes call? Well, the first thing, and let's also imagine this box is being successfully pulled, so it is moving up that way with a speed of v. Now, what forces do we have? Well, we've clearly got a force that's to do with the rope itself. So we're pulling it. And anything that we're pulling, well, that force is called tension. I can't write this. So tension. So whenever you have a pulling force, we tend to call it tension. Anything under tension means it's being stretched. The opposite of tension is called compression, which you might meet at various other points. Now, if the box is moving and it's moving up there, then there's also an opposing force. Anything in motion has drag forces and frictional forces. We're going to assume this box isn't moving fast enough to truly worry about drag, but we could identify that there is friction. Where does friction occur? Friction is always between the contacts. So right there, that is where we would identify the frictional force. And annoyingly, I want to move that slightly out of the way because I'm going to move that to there, and I'm just going to connect that up. That's the friction force. Frictional force. It's opposing the motion. So it does actually come into play before the thing is moving as well. If you're just pulling it, there's a thing called static friction and kinetic friction based on whether it's moving, but it's just opposing whatever the tension forces are trying to make it do. We also have another force, green this time, which is what we will call the normal. So it's called the normal contact. Normal contact force. I'm often a bit lazy. I just call this the reaction force. Basically, sometimes this will get listed as being an N or sometimes an R. I call it the reaction force because it's really arising as a result of Newton's third law, because it is a reaction to the final force that we would say is on this thing, which will, let's go in gold, is the weight of this object. Now the key to start with is where have we drawn these things and why. Okay, so tension, very simple. We've drawn the tension in the rope because it's the thing pulling it. Friction, we've drawn the friction as being between the contacts of the surfaces that are rubbing together. The normal, as we've noticed, is drawn at a 90-degree angle to the surface that we're sitting on, and it's coming from the surface. So it's that hill, that ramp, that is pushing up on the box, so the force is happening there. We direct it to be there. The weight is the one that we're going to be then interested in, and if we look at where we put the weight in, we draw the weight as being sort of, for this box, somewhere in the middle, acting vertically downwards. What we're going to do is sort of hone in a little bit on why we draw it there and the times at which it might not be there, because we have to pick a position to say these forces are acting, and because these forces are vectors, we have to be able to combine them with like vectors, which means that exactly where we say they're working does actually become important if you go into it far enough. But the key is that when we draw the weight of this box, we're not drawing it at the bottom of the box or at the top of the box, we're kind of drawing it in the middle. And we'll consider that because what we need to think about is something called the centre of gravity. Why do we not draw it there, or up here, or down there? We pick a specific point. We say the weight is acting there. We are picking a position. And that is because we need to think about something we call the centre of gravity. So in order to study what we call the centre of gravity, we need to think about certain objects. So let's go back and take this box. We're just zoomed into the box. We're just putting it sort of like deeply in space now. We say it's somewhere near the Earth, and we would say, right, the centre of gravity, we'd say mg, roughly in the middle it is. But we've got to think, why do we pick there? A box is made up of particles, and you could argue, but there is weight acting on every single one of these particles. All these particles, all that's happening really at the moment is I'm just making this box look spotty, but every single one of these particles has a weight because they all have a mass and the Earth is pulling down on all of them. And the thing is, this becomes complicated to solve. I can't be bothered to solve this. I don't want to solve mg for every single particle that's in a box. It's not of interest. It doesn't help me understand the physics. It doesn't help me predict what's going on. It's much easier to think about, well, what is the overall sort of like combined effect of all these things? And that is what the centre of gravity is. That is a terrible thing. I'm just going to just delete it entirely. That was horrible. So the centre of gravity is just simply a sort of an average, if you like, a mean of where the weight of that object appears to act. If you essentially took all of these different things and tried to make it so that all of them acted through one point, what is the net grand sort of total of all these forces, all these different things acting in one point, and putting them together, if this is going to work, it's probably going to be fantastic. What you end up with is a sort of a net thing that happens in one spot. This is becoming a bit boring now. Don't know why I keep doing this. You get the idea. I'm just going to delete them because they're just getting in the way now. So it is basically the average is this. Let's put it all into one spot and let's deal with that problem. Meaning I can deal with one place, one position in this object, and not deal with all of them. And why does that become of interest? Well, it becomes of interest for a few different reasons. One is if I throw something. So let's say I'm going to take this box and I'm suddenly going to throw it. Okay, and I'm going to throw it like a projectile. And the thing is, you know how projectiles behave. You know, you draw your thing, you have your angle, you draw your thing, it's like, 45 degrees, and it's going to fly like that. But when you've got a two or three dimensional object that's actually got a physical size, what is going to fly like that? What is going to do this? What happens if my box is rotating? What happens if I just, throw it in a sort of clumsy fashion? What is the thing that follows this lovely path? Well, it turns out it is the point at where we have the centre of gravity. The centre of gravity, or the centre of mass, will follow that lovely path, even if the box itself isn't. And there's a video that's linked to this, which is from MIT, where they throw things that are even weirder, like tennis rackets. So if we suddenly think about a tennis racket, why did I pick a tennis racket? Tennis rackets are easy. Tennis rackets are slightly sort of they aren't symmetrical, nice symmetrical objects. Also, they're things that people tend to throw and spin because they want to throw them up by the handle and catch them. But we have to consider, where is the centre of gravity of an object like a tennis racket or a frying pan or anything like this, where it's not symmetrical. We have a nice symmetrical sort of like head unit, but the centre of gravity is probably likely to be somewhere around here, because we have a sort of a solid bit at one end and the other bit is quite light and is mostly empty. Throwing a tennis racket through the air is a complicated motion. It's rotating, bits are going to everywhere. It's hard, but the centre of gravity of that, well, that will just follow a nice projectile motion, irrespective of what everything else is doing. And so this becomes, there's a reason why this becomes actually quite nice. There's a common sort of gag, I guess it would be, about how we often assume in science that things are spheres. And the reality is, in physics, it's a pretty good assumption. If you zoom out from anything far enough away, it's essentially going to become a dot. So essentially what we can do is, rather than worry about what's happening to the tennis racket, we can just worry about what's happening to the centre of mass of that tennis racket. And so what we can do is say, okay, well, I want to know what that bit's doing. Because if you know when the centre of mass is going to hit the ground, you're going to be accurate to within a fraction of a second when any other part of that object is going to hit the ground. If you know where the centre of mass is landing, then what it means is that you know within the width or the size of the tennis racket itself, you know how big that space is going to be. So you can work these things out. And that becomes perfectly reasonable for doing these kind of calculations. It's a simplification. Now, there's another reason for wanting to know about the centre of gravity, or the centre of mass. I'm using those two terms interchangeably, even though they're not exactly the same thing. But let's consider what happens when we have a table edge. And we have an object. So we have our block, and we're going to move it. We're going to move it over the edge of the table. Now, eventually, what will happen, as we move it, eventually what will happen is we'll get to a point where we tip over the edge of the table and suddenly we tumble down. And the centre of gravity is what enables us to work this out. And this deals with something we'll cover, which is problems of moments. You might remember that a moment, cut it, I think, so that we have a moment. We will cover this more formally, but a force times a perpendicular distance from a pivot. Well, in this case, that's our pivot, and the force is the weight, and where it's going to act, well, it's going to be acting through the centre. It's going to be acting through the centre of gravity. So let's draw that there. And essentially what we'll have is as long as that centre of gravity is this side of the pivot, well, our moment is taking us through the table, which means that we aren't going to fall. If we move our centre of gravity to the right of that corner, the pivot, well, suddenly we now have a turning moment and we're going to fall down. And that becomes of crucial importance if we're going to work out whether something is ultimately stable. And whenever we want to worry about a more complicated problem, where we have to consider the weight. So a simple moment problem that we'll start with, you might remember balancing seesaws and things. If we want to start accounting for the actual weight of the object itself, we need to know what the moment's going to be as a result of its own centre of gravity. Whether that is something on the edge of a table or a drawbridge or anything, we're interested in what is the moment that exists simply as a result of that object existing. And that is one of the other reasons for being interested in what we call the centre of gravity. It simplifies all the problems that we want to deal with. It deals with the problems of projectile motion. We just have to worry about one point on this object, not on everything. And it simplifies things to do with moments. And there's this particular here has also something to do with something that everyone has done at a certain point. Now, I'm just going to draw this. Because everyone, no, that is not good enough. Can't do this. Everyone has done the following. Everybody at some point has done what you've been told not to do, which is to lean back on your chair. Okay? Now, when you do this, you are creating a pivot at the bottom of base of that chair, in line with that back leg. Please don't do this now. I can already imagine that some of you are trying to, and you're going to fall over because you're going to keep pushing it too far. Now, what happens is that you have a centre of gravity. And for a human being, it's probably somewhere around about here, let's say. And that centre of gravity of you and the chair, it's actually probably not quite there. It's going to be further forward. I don't know why I've drawn it there. remove that person's heart. That's not very nice. So the centre of gravity for this person is actually going to be probably sort of slightly outside of them. It's going to be about there, because they've got this, sort of this area of their legs sort of is forward of them, out of their line. So the overall average centre of gravity, it's somewhere about there. So what we can say is that this person has a centre of gravity mg, which is acting down. Now, we all know what happens when you push back on a chair and get to this position. You either tilt forward or tilt backwards. And it's all about, where is this centre of gravity acting? Is it to the right-hand side of this pivot point? Is it to the right, in which case, fantastic, you're going to fall that way. Or have you tilted yourself far enough obviously this is quite extreme, where suddenly your centre of gravity is pulling down here to this side of the pivot, and so suddenly you're going that way. Congratulations, you're falling over. And what is it everyone is always intending to try and do when they do this silly thing? Well, they're always trying to balance themselves so that their centre of gravity is lining up, essentially in line with that base leg, because that is the point at which there is no moment either side of you, and so you will stay balanced. And that may seem silly for people. What's the value of doing this? What's the value of doing this? Well, in terms of this, there is actually none. This is not a valuable exercise. There's no value in knowing this whatsoever at all, because this is just a silly thing that children do and eventually will get it wrong. But there is value in understanding where the centre of gravity is for different objects and how that affects whether or not they're stable, because this sort of exercise is an exercise in stability. If you tilt anything, there is a chance it will topple, but it will topple the moment that the centre of gravity goes beyond part of the pivot, that exterior bit. So any form of object that's on a slope or is tilted, the centre of gravity is of key importance. As long as the centre of gravity, as long as that line, if you draw a line straight down and it acts inside that object, well, then it's stable. But the moment you make it more tilted, the centre of gravity, the moment that centre of gravity acts outside of that object, suddenly you get a moment and that object is tilting. And this is something that people have to check. They have to check it for various things, particularly for transportation that people ride in, things like buses. They have to be tested. And what we want you to do is to watch a video called the Aldenham Bus Test, which is the next link in this, because it'll show you just how weird, how stable buses can be, even double-deckers, and how much they have to be tested in order to make sure that their centre of gravity never falls outside of their wheels. So that's what the centre of gravity is. So go and watch the Aldenham Bus video, and then you can come back to this bit. So what we have, having watched that video in the example of the London bus, it's quite impressive that they can take up to 34 degrees before tilting over. Now there's ways in which they design it to do that. Buses are very big, and the reason you've got to be careful is they have a lot of people in them, but there are many forces that you can act at various things. If you have wind sort of coming in, so you've got wind that's buffeting a bus, you've got a force at the sort of the distance, you've got a force acting at this sort of perpendicular distance, you end up with a moment that's trying to push the bus in that direction. And the idea is that may cause the bus to tilt very temporarily. It's a big push, there's a big buffet, maybe the bus slightly tilts by a couple of degrees. But the idea is that because the centre of gravity is so big and is sort of there, what that will do is always provide a counter moment to whatever it is you do, whether you go on an angle or whether you go at an angle, you get buffeted by wind, or you end up in a spin or something. Anything that might cause the bus to tilt one way, the centre of gravity will always pull it back to the ground in a manner that you want it to. And this is what we call a stable equilibrium. Okay? It's got its position, which is the two wheels on the road, and it's going to remain there. It's stable. If we return to the wonderful example of the person tilted on a chair, this is an example of an unstable equilibrium, because any slight deviation from this key thing where the centre of gravity is directly acting through that singular pivot, any movement left or right is going to cause the chair to tilt and swing dramatically backwards or forwards. And so those are two different types of equilibrium. Now, how do you achieve big things having a big stable equilibrium? Well, there's things you can do. The first is you want to have a really wide base to make sure that your centre of gravity is less likely to go out of it, outside of the base. And the second thing you can do is you can add weight to the bottom of the bus to pull the centre of gravity position down, to pull it down to, say, here. Because a lower centre of gravity is much more stable. It's much harder to move. You have to go to a bigger angle before that will move outside of the confines of the actual block. Whereas something which has a very high centre of gravity, so if it was up here, would be much easier to move. And this is something you actually do see whenever you see people attempting to hold position. If you watch people playing sport, say for example rugby, and they're attempting to adopt a position which means they won't get pushed over, you go low. You brace yourself, you spread the legs, put the legs far apart to try and give a big wide base, and you sort of crouch down. And what that means is that you're much harder to knock over, because it's much harder to push your centre of gravity outside of the basis of where your feet are planted. Because once you do that, then you're going to tip, and there's not a lot you can do beyond try and move your centre of gravity the other way. That isn't something you need to know for the course about the stability. It's just a kind of an interesting fact. So the final thing that we're going to then have to think about is, well, how do you find it? Okay, how do you find the centre of gravity? And there are two types of scenarios that might exist that might be particularly helpful. The first is if you've got an entirely symmetrical object. So if you've got a symmetrical object, fantastic. And it's symmetrical not just in terms of shape, but in terms of its density and therefore the mass distribution. Well, that just means that it's just going to be along the lines of symmetry. The centre of gravity is basically going to be here. That's just what it is. And for most blocks that we put on, onto ramps and things, that's what we can assume it is. It's just right in the centre. A slightly more interesting thing happens if you just happen to have something which is a bit of an odd shape. So something like this. And this is something which actually is where you start needing to build it and suspend it. If you suspend any object, so you sort of poke a hole in it, you might remember doing this. You poke a hole in it and you allow it to suspend. So you have what we call a plumb line, which is a line which is basically just a mass on a piece of string that's just going to hang vertically. If you suspend it, then this thing will rotate. And what will happen eventually is, I forgot, I shouldn't have done this one. I can't draw this again. What will happen is wherever the centre of gravity is, let's assume on this one, it's going to be about, let's say it's about here. This thing will rotate until the centre of gravity is hanging vertically. So any object that is suspended and has been allowed to freely rotate, to freely swing, the centre of gravity will be somewhere in a line straight down. And if you do that in a second point as well, and you find that it suspends, say, that way, completely vertically, when you suspend it like that, then where those two things cross, that's where your centre of gravity is. You can test it with a third thing as well, So it just basically means that is where your center of gravity is. Any object that's freely suspended will hang, and its center of gravity will be just vertically straight down. And that works even if you design a three-dimensional object or an object with a non-uniform density or anything, or what appears to be there, a weird, horrible attempt to draw the Batman signal. So that's how you can find the center of mass. You poke a hole in it, let it suspend, let it freely suspend, and see what you get. And that is what we do with the center of gravity. So, excellent.